the top, or?
Yeah, just right from the top.
Okay. So, the measure of an exterior angle. You're going to have to excuse me. I have a really bad cold, so I may go into coughing spells.
Mm-hmm.
All right. So, how are we going to do this one? A.
So, we could do 360 and then divide it by 3 and then subtract it from 180.
Okay. That works. And what are we going to do with B?
The same thing. We just divide 4 by 360.
Okay.
And subtract it from 180.
Okay. We're going to do all 5 of these exactly the same.
Yes.
Okay. So for number 2, what are we going to do?
For equilateral, equal angular, a pentagon just divided by 5.
Well, you got to know the total sum of the angles.
Mm-hmm.
So it's n plus 2 times 180. There's the sum of the angles divided by n, number of sides. So for a pentagon, it's 7 times 180 divided by 5. For a hexagon, or excuse me, pentagon is, okay. A hexagon is 6, so n is 6.
So 8 times 180 divided by 6.
Yeah. The first one would be 7 times 180 divided by 5. Second one's going to be 8 times 180 divided by 6. Third one is going to be 11 times 180 divided by 9. So forth and so on. In other words, the number of sides is that plus, actually the number of sides is this number right there. And the numerator is always that number plus 2. All right.
Mm-hmm.
All right, number 3. On the number of sides of an equiangular. These are the words he should have been using in that last section we went over that he didn't use. He kept saying polygons when he meant regular polygons, unless I'm mistaken, but now he's using the correct terminology. So, kind of, here, let me write that so it doesn't cover up a key part of the question. So if each exterior angle is 60 degrees, what kind of polygon is it?
So it would be, the interior angles would be 120 degrees.
Let's work more with, it's actually easier problem if you stick with the exterior angles. You know what the sum of the exterior angles is, right?
360.
So if one of them is 60, how many sides does that thing have?
Oh, 6, so it's a hexagon.
The next one.
360 divided by 40. It's 9, so that's a nonagon.
Okay. So you get the picture on these.
Yes.
Okay. Let me scroll down a little bit here. And if we happen to have time, we can do that last problem we didn't get to. Which I did figure out. 55 degrees was that angle. on that last problem of the previous section.
Yeah, we went over it in class.
Yeah, it's just a series of equations, simultaneous equations is what it is.
Mm-hmm.
Once you write out all your equations that you know, then it boils down to two simultaneous equations.
Mm-hmm.
Okay, so this is a regular pentagon. How do you prove that triangle PNT? We're trying to prove that that equals that.
Mm-hmm. Well,
What's our strategy going to be, do you suppose?
the proving that angle ENT is equal to ATN.
How about proving that triangle 1 is congruent to triangle 2?
Yeah. Yeah.
Okay, so if we can prove that, then we will know that those two sides are equal.
Mm-hmm.
So let's work on proving 1 is equal to angle 2. Triangle 1 is congruent to triangle 2. Why?
Well, we know that EN is equal to AT and PE is equal to PA. And then we also know that angle PEN and PAT are equal because regular polygons
Yeah.
are equal.
So therefore, that makes them congruent based on what?
Side angle.
Sine, angle, sine, right? Side, angle, side. And because they are congruent, then this one equals that one.
Mm-hmm.
Okay. Whoops, hold on. Aha! A stop sign problem. Is it scalene, meaning 3 different sides, 3 different angles? Isosceles, equilateral, or undetermined?
We don't know if all the sides are equal.
See, here's another. Actually, in a stop sign, it is a regular polygon. So I don't know if we're supposed to know that or not. He could have said in the regular octagon shown is that thing. So let's change that because I think that's what he meant. In the regular octagon. Because otherwise we're not going to be able to solve this problem, if you notice.
Mm-hmm.
If we didn't know it was regular, we would not for sure be able to come up with any information on that inside triangle.
Mm-hmm. Then it would be undetermined.
Right. But we do know it's regular because stop signs are regular octagons.
Mm-hmm.
So what does it tell you? Which two figures are congruent?
Two figures?
Uh-huh.
The two, trapezoids?
Exactly. Trapezoid 1 and trapezoid 2 have to be congruent if it's a regular octagon.
Mm-hmm. Which
makes that triangle what kind of a triangle?
Isosceles, because NE would be equal to NT.
Okay. Now, is there any way that TE is equal to NE or NT?
No.
If we compare that thing in there, which is not a trapezoid, it's a triangle.
It's not. Because it's not.
I would say it's not for sure, which the only thing we can then determine is that one, or rather that, is equal to that, and we have an isosceles triangle.
Mm-hmm.
Definitely not scalene, it's not undetermined, and because of this part here, it's not equilateral.
Mm-hmm.
In an equilateral or equal angular polygon, measure of each exterior angle is 25% of the measure of each interior angle. What is the name of the polygon?
Mm-hmm.
Let's draw us a hexagon. Only because that's the easiest thing to draw in terms of regularity. For me, is a regular hexagon. What they're saying is that angle X is equal to 0.25 X, being that angle and that angle. They're not equal, right?
Mm-hmm.
So I can say X is equal to 2.5X.
Isn't it 0.25x? Yeah.
That's what I meant, 0.25X.
Sorry, I just wrote that down. Sorry.
No, that's all right. No, I never feel bad about correcting my words, especially when they're wrong. Measure of the exterior angle. Exterior angle is going to be X, is equal to 25% of the measure of each interior angle. Okay, so that looks right. What is the name of the polygon? If we call n the number of sides, what can we do? What is X going to be?
X.
If it's a hexagon, we know that n is 6. Can you figure out X if you knew that n was 6?
So it would.
Right?
Mm-hmm.
So X is always
It's always out of 360.
360 divided by n. Okay?
Mm-hmm.
Right?
Be a fourth of 360.
Well, let's just go substitute exactly for X. Let's substitute it in terms of n. So on the left side of this equation, we have 360 divided by n. On the right side, we have a 0.25 times 360 divided by n. Multiply both sides by 4. And you have 1440 divided by n equals 360 divided by n. Nah, it's not getting us anywhere, is it?
Mm-mm.
I find this a lot in geometry, where you start writing equations and you end up with an equation that isn't solvable. So let's go back to the beginning. This thing on the left is true, correct? X equal 0.25 of x? Has to be?
Yeah, because if it's 25%, that's
Right. Of each interior angle. And here, x is equal to the exterior angle. All right. We also know that if we take the exterior angle, n is equal to 360 divided by x. Not the way I wrote it. Do I have that correct? Let's see. If we have an exterior angle of 90 degrees, we have a quadrilateral. N would be 360 divided by 90. If we have an exterior angle of 120, we have a triangle. So that's definitely correct. Now, does that help any? If I plug in, that makes x equal 360 divided by n. So we have the same problem, don't we? Actually, how can x be equal to a quarter of x? Here's what we know, right? Is that the sum of those two angles, x plus 0.25x,
equals 180.
180, yeah. So now we have our two equations and two unknowns. Let's forget all this garbage over here. So that gives us 0.5x equals 180. X equals 360. How can an interior or an exterior angle be equal to 360? It can't be.
Yeah, it would have.
Does not exist. No matter how many different ways I try to solve it, I get an unsolvable problem. In other words, that's true according to sentence 1, and that's true according to linear pairs. All linear pairs are equal to 180, right? And you can't have both of those true at the same time, because you end up with x being equal to 360, and you cannot have an exterior angle equal to 360. I'm going to go with does not exist, and let's go on. I got a feeling these are not going to get any easier, huh?
No.
Prove that the perpendicular bisector of a side of a regular pentagon passes through the opposite vertex. Now let's start with a equilateral triangle, only because that's the smallest. Oh no, we're doing
wouldn't we start with pentagon?
Actually. Pentagons are always hard for me to draw.
Just try house.
Well, that's not a regular pentagon, believe it or not. There's the house. Notice that's not regular. Those are 90-degree angles. Those are not. Okay? So we got to draw a regular pentagon. Well, what do we know about a pentagon? It's got 5 sides. It's 540 degrees. So each side is 108 degrees. So we basically have to draw a figure where each side is the same length and it's 108 degrees. There, something like that. It's not quite right, but it's closer than a house. Okay. Now, prove that the perpendicular bisector of a side passes through the opposite vertex. So I'm trying to prove that a perpendicular bisector of that side goes through there. Well, how are we going to prove that? What's the essence of proving all of these things?
Prove that the two
The 1 and 2 are congruent.
Yeah.
That would force that line to go through the vertex of the other side. Well, we know that side's the same as that side. We know that angle is the same as that angle. We know that all of these sides are the same. Not quite. Each of these other ones is double that one. So we got to put a little thing like that. Okay. And the diagonal is equal to itself. So we have a 1, 2, 3, 4. We have a quadrilateral on the left. Number 1 is a quadrilateral that all sides are equal to another quadrilateral, and one angle is equal. More than one angle are equal. That angle is equal to that angle. That angle is equal to that angle. So we have two quadrilaterals that have side, angle, side, angle, side. Side, angle, side, angle, side. Angle, side. If that's not congruent, I don't know what it is. But in other words, I don't know the theorems that prove
I don't know the theorem to prove quadrilaterals.
But surely if you have side, angle, side, angle, side, angle, side, that's got to prove congruency. So, if you prove that 1 is congruent to 2, then that diagonal has to go through the vertex. Can you generalize about the perpendicular bisectors of the sides of regular polygons? Well,
if we draw a triangle, it works for that.
Okay. So it doesn't ask us to prove it. It just says, can we generalize it? Well, it works for a pentagon. It works for a triangle. How about a quadrilateral? How about a square? Does not work for a square. So what do you suppose our general theorem would say? If it works for a triangle and it works for a pentagon, but it doesn't work for a square, what do you suppose is going on? Here, let's draw one more figure, because I can draw these. The hexagons are really easy to draw. This is where you kind of draw it as a house, only the bottom of the house is like that. Okay, so, nope. Perpendicular bisector does not go through the vertex. Perpendicular bisector does not go through the vertex. So what do you suppose the generalized theorem would be?
Perpendicular bisectors.
If it has an odd number of sides, that is true.
Oh.
If it has an even number of sides, it's not true. But it's true for a triangle and it's true for a pentagon. I'm going to guess that it's true for a septagon and a nonagon also. So the generalization would be if n is odd.
If n is odd, then the perpendicular bisectors bisect the opposite.
Go through the vertex of the figure. Okay, in other words, the opposite vertex. That's what we're trying to prove or generalize about. All right. Let's have a look at the other picture here. So that's a right angle, and we know that that is the same as that.
Mm-hmm.
And we're trying to prove that AEF is isosceles. This could be tricky.
Mm-hmm.
Well, the best way to try to do these problems is to what? Where do I start?
With another one of the triangles.
Well, how am I going to prove that that triangle is isosceles?
The two of the sides are.
Which two are they going to be?
You
can look at it and see.
A and E and F and E.
Yeah, FA and AE. So that's what we're really trying to prove is that AF is congruent to AE. That's what they really want us to prove.
Mm-hmm.
Now, how can we do that? Think for a minute. Let's see. We know that that is the same as that. And we know this is a right angle.
Mm-hmm.
So this triangle is isosceles, right?
Mm-hmm.
Which makes that equal to that. In other words, B is equal to D. This one is equal to that one because they're vertical angles.
Mm-hmm. All right.
So what do we have? We have these two are congruent, right?
Yes.
Yeah, we know that, I think. Why do we know that? Hold on. Sometimes
Why do we know?
Start from the back. It's easy to get, you start using that and trying to prove what you're trying to prove. I know that D is equal to B. And I know that B plus F equals 90.
Mm-hmm.
B plus F equals 90.
Oh, if B and D are equal and C is 90, then it would just be 45. So B and D would be 45-degree angles. And then if we know that
Well, now hold on. No. B is equal to D, but we don't know that this angle up top, A, is 90. How do we know that's 90?
we know that C is 90.
Right.
Oh, never mind.
That's not in that same triangle. That's in a different triangle. In other words, we don't really know that B is equal to F. I think this solution is going to ride around proving that this top little triangle is equal to the bottom little triangle. Or congruent. Not sure how we do that. Let's see. B is equal to D. B is equal to 90 minus F. Therefore, D plus F equals 90. B plus F is 90 for sure. B is equal to D for sure, which makes D plus F equal to 90. Let's see. What can we do to prove these two triangles are congruent? These two triangles, 1 and 2. And will that solve the problem? Let's see. We're trying to prove that AEF is isosceles. Means we need to prove that AF equals AE. AF equals AE is not going to depend on those two triangles being congruent unless we can prove that that one is isosceles.
Mm-hmm.
But ultimately, we have to prove that that side's equal to that side.
We know that FEA is a vertical angle of DEC.
Right. These two here are definitely equal. Again, this looks like one of those problems where you could write down a bunch of equations. In other words, I know that b plus f is equal to 90. That's an equation I can write down. I know that AB equals AD. That's an equation I can write down. I know that BF minus AF, or BF minus BA is equal to AF. And AD, let's try that. I think that's going to get us to our solution. BF minus AF equals, minus AB equals AF. Okay? True statement? And also, AB is the same as AE. So I can say BF minus AE. No, that's what I'm trying to. AD. So this has to be true because AB is equal to AD. And then you could write down all these little equations like AE plus ED equals AD. Does that help? It gives us BF minus AE minus ED equals AF. We're trying to prove things about AE and AF. This actually seems like it's probably in the right direction. BF minus AE. Okay, because BF is equal, or AB is equal to AD. That is true. How do we know this is true? AE plus ED equals AD? We don't know that that's true, do we?
We don't.
Let's erase that. Last thing in the world you want on here is things that you don't know to be true. I don't know. I think we've spent enough time on this problem. Maybe we can pick this one up next time we talk. Let's go on to the next problem. I hate to kill a session with a problem that I don't know how to do. And I'll bet you the rest of these are easier. The reason I can tell is because there's no figure in the picture.
Yeah, I hate
right?
proving.
In other words, you're going to automatically know that 10, 11, and 12 and 13 are going to be easier than number 9. Given 9 had a complicated diagram and we weren't able to make much progress on it. So, let's go to 10. What equation can I write?
N minus 2 times 180 over n.
Well, first of all, what is 10 minus 2 times 180 equal?
We don't know how many sides there are. Oh, polygon.
50, 40.
Oh, yeah.
In other words, that's the starting equation that we can get from the sentence they have given us.
Mm-hmm.
Now, do you have your calculator? Divide 50/40 by 180.
50. 28.
So n equals 30. You always want to start with that fundamental equation that applies to all polygons.
Mm-hmm.
Or regular polygons in this case. Okay, here number 11. The sum of polygons angle measures 9 times. Well, let's see. What is the polygons
Equal.
Again, he doesn't use the word regular.
Mm-hmm.
Should have studied a little reg. The sum of a regular polygon's angle measure, which is that, is equal to 9 times the measure of the exterior angle. Equals 9 times, what's the measure of the exterior angle?
Of a regular.
360 divided by what?
360 divided by 6.
By n. Oh. This is confusing. Tells you the answer right there, doesn't it?
No, because the other one is 9 times that of a hexagon.
It's 9 times the measure of an exterior angle. Oh, okay. So this is not an equation, that's a number. Exterior angle of a regular hexagon is 60. So it's that. So we end up with n minus 2 times 180 equals 540. We got n minus 2 equals 3, n equals 5. So we're dealing with a pentagon. And I was wrong. You don't need the regular. In other words, any pentagon, this is going to be true.
Mm-hmm.
Not have to be a regular pentagon. What we know is that a pentagon, the sum of the interior angles is 540, always, whether it's regular or not. The fact that it references a regular hexagon merely tells us that it's 9 times 60, so we can figure out what it is.
Mm-hmm.
But this pentagon is not necessarily regular. It does not have to be regular. Or the polygon they're talking about. That polygon does not have to be regular. All right, 12. What's the name of an equiangular polygon, which means regular? The ratio of the measure of an interior angle to the measure of an exterior angle is 7 to 2. Well, let's just draw, see. There's the exterior angle. We'll call that 7x. And there's the interior angle. It's 2x, is that correct?
I think the interior is 7x.
You're right. Can we solve for x?
Yes.
How?
I just put a variable.
No, we can solve it directly from that. What's the sum of those two angles equal to?
9x.
And what do we know what's this angle from here to here?
180, so 9x equals 180. So it'd be 180 divided by 9.
Okay. So we know that the exterior angle is what?
It's 20, or x equals 20, so the exterior is 40, so the other angle is 140.
Well, once you get the exterior angle, we can answer the question. How many sides does this figure have if each exterior angle is 40 degrees?
So 360 divided by 40.
Uh-huh. 9.
9, so it's a nonagon.
Nonagon, exactly. A nonagon, those would be 40 degrees. Those would be 140 degrees. That's a 7-to-2 ratio.
Mm-hmm.
So you can kind of see that figuring out all of these problems is pretty much these couple of equations. In other words, n minus 2 times 180, that's a key one. And 360 divided by n gives you the measure of each exterior angle. All right, let's look at this. If the number of sides of an equal angular polygon is doubled, the measure of each exterior angle is halved.
That is always true.
Yeah. In other words, if I take this from a 3-sided to a 6-sided, the exterior angles go to 60. Measure of an exterior angle of a decagon is greater than the measure of an exterior angle of a quadrilateral. What happens to the exterior angle as the number of sides go up? Does it go down or go up?
It goes down.
Okay. So a decagon has more sides than a quadrilateral. Therefore, the measure of the exterior angle is never greater.
Greater.
So that's an n. And we didn't even need to know much other than which figure does a decagon or a quadrilateral have more sides. And that's all we needed to know.
Mm-hmm.
And so we don't really need to know how many sides a decagon has. We just need to know that it's more than a quadrilateral.
Mm-hmm.
Okay. A regular polygon is equilateral.
That is always true.
And the equilateral polygon is regular.
That is not always, so that's sometimes true.
Give me one that isn't.
Like a rhombus, it has all the equal sides, but it doesn't have all equal angles.
Very good. If the midpoints of the sides of a scalene quadrilateral are joined in order, the figure formed is equilateral. Well, a scalene quadrilateral. There's a scalene quadrilateral, I think.
Mm-hmm.
The midpoints are joined in order the figure formed is equilateral. My concern is, see, it's not always true, right?
Mm-hmm.
Because it's really easy if I want to draw this figure slightly different. Now if I join the midpoints The figure formed is equilateral, meaning all four sides are the same. Let's draw the figure really strange. But sometimes the secret to these problems is drawing the figure such that you can tell for sure there's a scalene quadrilateral. Daggone it, that thing looks equilateral also. So I suspect the answer is true. Question is why? Yeah, they don't really ask you to prove it. So if I had to answer this with no time remaining, I would draw that merely because I've drawn 3 different quadrilaterals and they all seem to produce equilateral quadrilaterals. Question is why? Why is that side the same as that side, the same as that side, the same as that side? Well, we know that's the same as that. I know that is the same as that. So forth and so on. Oops. Let me just draw this a little bit bigger. Maybe we can get an idea why this is true. And why does it have to be scaling for this to be true? This is really an odd geometry problem that I don't understand why it's true.
But it looks...
Yeah, it certainly looks true no matter how I draw it. The only thing we know for sure is that that's equal to that. That's equal to that. That's equal to that.
What if we prove that all the triangles on the outside were equal? But they're not.
All the triangles, they're not, no. They do have one side that's all equal. In fact, they appear to have 2 sides that are all equal. In other words, if indeed this quadrilateral in the middle is equilateral, then triangle 1, if I label these triangles, notice that triangle 1 and triangle 2 have 2 same sides. In other words, it's side, side. Well, we don't know that it's 2 equal sides. That's what we're kind of trying to prove. In other words, if the quadrilateral in the middle is equilateral, then triangle 1 has 2 of the same sides as triangle 2. The question is why? Know that each of these hash marks are not the same. In other words, 1 hash mark is definitely not the same as 2 hash marks, because otherwise it wouldn't be scalene. This is another one I'm going to have to get back to you on. This is a tough problem. It's a good one, though. I like this problem. I feel like if we had enough time, we'd probably be able to solve it. Although I don't know. I'm not sure about that. I can't really figure out how we're even going to proceed.
Well, how do we know it's equilateral?
Well, we don't. We don't. That's what they're asking us. The thing is I've drawn 4 different types of scalene quadrilaterals, and
they all
every
look
one of them seems to produce an equilateral quadrilateral in the middle.
Mm-hmm.
Which means that has to be equal to that, has to be equal to that, has to be equal to that. And if that's true, then triangle 1 and triangle 2 have 2 equal sides.
Mm-hmm.
But they're not congruent. They're not similar. So I don't know how you could work backwards to prove that triangle 1 and triangle 2 have 2 equal sides. That doesn't seem to be the way to go. Because I know of no geometry that would prove that.
Mm-hmm.
I think this might be one that we have to get back to, only because I have no idea how to really proceed.
Mm-hmm.
Yeah. I don't know.
Mm-hmm.
Let's just take a look at the last one. I know we're out of time, but we've got a few minutes. If the midpoints of the sides of a rhombus are joined in order, the figure formed is an equilateral but not equiangular.
Huh?
So now the question becomes, is on the previous question, did it have to be a scalene quadrilateral? Or could it have just been any quadrilateral? Because this one certainly is not a scalene quadrilateral, although they're asking us to prove that it's equilateral but not equiangular. Well, proving it's equilateral is going to be a piece of cake, because we know that's equal to that, 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 equal to that.
Mm-hmm.
And this angle equals that angle. So in this case, we do have congruent triangles, which makes that equal to that. And I can certainly prove that this is equal to that based on the same reasoning, but I haven't proved that it's equilateral yet.
Mm-hmm.
Joseph, I need to look at these 2 problems and see if I can stare at them. Sometimes with geometry, I can remember one student that had the hardest problem I've ever seen, couldn't figure it out, closed out the session. I went down on my couch and I started picturing this thing in my mind, not on paper, but in my mind. And I solved it that way. But it took me about 20 minutes of staring at it. And unfortunately, that's the only way to solve some of these problems. You just have to look at it a long, long time and see if you can see something that you're not seeing.
Mm-hmm.
And I would say these 2 problems are probably good examples of that. So let me look at these a little longer. Maybe I'll have some clues next time we meet. Although usually you have the answer by then. So nonetheless, I'll look at it and see if I can't come up with some revelation.
Mm-hmm.
All right? All right, Joseph.
Yep.
I will talk to you next time. You have a good weekend. Talk to you later.
Okay, thank you.
Bye-bye.